Okay, recording now.
Cool.
Admitting the students. Turning myself to mute.
And Neil, you can just point to me when I should start because I can't see the numbers coming in.
I think we're at 48. So I think
Oh,
you can
wow.
just start. Yeah.
Then we can just start. Okay, welcome everyone to the fourth lecture in this course. So today basically finishes the first initial bit of the course where we have pretty much tried to do machine learning in 2 weeks. And this lecture is going to cram in everything that we haven't really talked about. So it's going to be a little bit less in detail. And then next week, we'll start with the material that's more special for this course. But there's 2 things that we haven't talked about that we need to kind of bring up, right? So it's the pink elephant in the room, and that is not all models are conjugates. Let's do some approximate computation. So we're going to hint a little bit at that, and we're also going to talk a bit about latent variables. But first, let's do a short recap of what we talked about last time. So the idea of non-parametrics was simply this, right? Rather than saying, I want to fit, say, a function, what I do, or some other object, I take my data, and then I parameterized some object, some function, some model. And then I now take this data and I update these parameters. And then I basically throw away that data and I can now use these parameters which fully parameterize, say, my function. So now we said that that's kind of tricky because how do you parameterize rich enough classes of models using in this way? So the other idea was to then go non-parametric and then say, actually, let's not throw away our data. Let's actually use a parameterization of the object, which is in the relationship of how any data point relates to the data that I've already seen. So now it's still a parameterization, but it's a parameterization not of the object directly, but it's a parameterization of the relationship between data. So we took that to a probabilistic setting over functions. And the way we did was simply this. What is it that I can observe of a function? What is actually my data? Well, the data, the thing that I can observe is the output location at the specific input location. Now we said that let's make those Gaussian. And then that leads to a massive Gaussian distribution, effectively, where we say that all output locations, F, are jointly Gaussian, distributed where they have a mean which is completely specified by the input location, a mean function, and a covariance function which is completely specified again by the input location to these. So now that provides me with what we call a Gaussian process. So that allowed us to do, because this was still a nice conjugate model, this allowed us to do samples from a posterior. So we could have data and then we could use that data and then we could do predictions that follows that data. So the idea was then all the time when we work with these, when we implement them, when we play around with them, it's just a Gaussian. It's just the normal Gaussian distribution that we look at different conditionals to do these predictions. But the theory is effectively, and this comes from the marginal property of the Gaussian, is that the way we can think about this object is that somewhere there is an infinite object called the Gaussian process. And now, by the marginal property, we know that if I look at any marginal of this, I get a Gaussian distribution, I get different Gaussian distributions, which are all consistent with this process. And that's really what a Gaussian process is. But when you're on the implementation side, you're always in this finite dimensional object. And then rather than simply just thinking, oh, so it's just, that was a lot of talk for a simple Gaussian. The way you should think about it, I think, isn't it really cool what you can do with such a simple thing as a Gaussian? So then let's look a little bit more in detail on the predictive posterior. So we actually looked at this where we plotted what these matrices actually were that builds up this. But let's look at the mean now. So what we can see is that the mean is exactly what we would expect from a non-parametric model. What we have here is that I got my data y. This is the output data of the function that I've seen. And then I got that multiplied with a matrix. And that gives me the new output locations at a point x star. Okay, so it's just a linear thing to the data. Now let's take the linear regression predictive posterior. I didn't show this, I just showed the top integral. But what this was, right, is that we took our posterior that we inferred, and then we took our likelihood, and then we integrated, we marginalized out the W. So that led us to this predictive posterior that we could use, okay? So now if we look at that, it's not really surprising what it would do. So the new locations, y star that we want to predict that, is some matrix times the input data of those locations. Well, that makes perfect sense, right? We learned the line, which was W times X is equal to Y. Now we've effectively learned a new line, which is some W, some weight times the data, what we want to predict that. But what we can do now is that we can do, and I hope I've done this the right way around, we can just do some linear algebra and move this around a little bit, and we can write it on this form instead. And I got them both on the next slide. So now if we look at the predictive mean for these two, we see that actually they both look awfully similar. They are both a linear thing to the output data. So it's some matrix times y, right? So let's now say that we take this linear formulation here, this linear, so the thing that came from the linear regression, and then we say, let's do the basis function interpretation instead. So that means that this product here is that we first map this data to using some basis function and take the inner product there. So now if you think of x as the center of each basis function, that means you have a basis function per data point, effectively. Now, let's say that you could parameterize this inner product, because the data here always comes x, 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 x. Say that you can parameterize that inner product itself as a function. Well, now, if you would do that, you would see that these things would look pretty much exactly the same. So what you have is you've got the data that you want to look at, the input location you want to look at, times the data that you've seen. That's pretty similar to that. And then you got in here, you got the data that you've already seen taken as an inner product. So if you would do that, this would then lead to the interpretation of a GP as an infinite set of basis functions, simply because I can see as much data as I want, right? So now this is a different way of arriving to Gaussian processes. And if Neil gave a link to Carl Rasmussen's book, and in that book there's 2 chapters, or possibly it's chapter 2 divided into 2 parts, where they first describe this way, which is called a weight space view, and in the second part they explain the equivalent function space view, which is the one I took yesterday. These two are really equivalent. They give you possibly different benefits. This one, the weight space view, might be a bit more geometrical if you like to think in that way, but they're both equivalent. So that's GPs. So then there's the next thing that we've kind of avoided talking about that we need to bring up, which leads to the material today. And that is the marginal likelihood. So we showed this slide a couple of times where we said, cool, we got our likelihood, our prior and posterior. We talked plenty about them, and hopefully we've shown this benefit of making hypothesis, taking data and getting an updated hypothesis. But then we got the denominator, which is the evidence or the marginal likelihood. And we've kind of avoided talking about it. So now we are going to talk about it. So what is actually the evidence? Well, so the evidence is this integral, which is taking all my parameter settings and I match them with the data so that it gives me a distribution over the data space. So I showed this graph, which I've now also updated to try and give an idea about it. So what the likelihood is here is that in this case, I have this line and I can only control the slope of the line. So it has one parameter. So to plot one of these distributions, I need to know the slope because this distribution P of y given W is indexed by the slope. Okay. Then I have my prior, here I got 3 different of them, where I got how I believe W to be, right? So now if I take each of these W's according to my strength of belief in them, and I average them out, I will get this distribution. And this distribution here is now the evidence or the marginal likelihood. So now this is a distribution P of y. So now the nice thing is that I could have had different models with different parameterizations, different priors. I can't compare their likelihoods, but I can compare their evidence. And this is what we're going to do a little bit later. We're going to see how we can use this potentially for model selection. But there's another hint or thing that I wanted to mention. So what is it that happens when we marginalize out a variable? Because this is the process of going from taking these 2 objects and we marginalize out, we integrate out W. You can see that the red, blue, and green give completely different behaviors on this with the same likelihood. So when we marginalize something, we don't remove the effect of a variable. We're doing the absolute opposite, right? The variable doesn't disappear. What we do is that we take in absolutely everything we know about that variable. So that's important. So tongue in cheek, I usually say this. If you want to really give someone a compliment, your friend, your partner on something, you should tell them you've completely marginalized them from your life. Because that means in anything you do, you take their every opinion into account. Cool. So let's take 2 models then and compare their marginal likelihood. So I'm going to take a linear model and I'm going to take a linear basis function model with, I think, 6 basis functions. My linear model is looking like this, so the same plot as before. And my basis function model looks like this, okay? I can't really compare the likelihood, I can't really compare the prior, but the evidence here is something that I can compare. So now we can see that these 2 models distribute probability mass in completely different ways. So now for data that would lie up here, this model will you say, you know what, I really don't think this data comes from this model. While if it's up here for this model, this one will quite like this, right? And vice versa for these 2 points. And the reason is that both these models actually place probability mass pretty much everywhere, or everywhere in this case. But because a probability has to sum to 1, if you place a lot of probability mass somewhere, you have to place less probability mass somewhere else. And this means is that a probability is effectively a zero-sum game. So if you think about models, and if you think about a model being good, if it places a lot of probability mass on some data, that implies directly it has to be bad at something else. So this notion has led to this quite famous graph. And this graph comes from David Mackay's PhD thesis. And Neil will mention David a bit more, but David was a professor here in Cambridge, which had an enormous impact on machine learning, both in this country and elsewhere. He was a very inspirational figure. So the idea of this plot is this. So if I now compute, I have 3 different models, M1, M2, and M3. And now I compute the evidence for these 3 models. Then I have a data space here on the x-axis. And now this data space is ordered such that down here I got data which is simple, and up here I got data which is complicated. Now, if this model here, M1, is a very simple model, it therefore places probability mass over less data sets, but it places therefore, because of the sum to 1, more probability mass at them. This model here is very complicated, so it explains a lot of things, but due to that, it also has a low probability everywhere. So now, if the data that I have is D0, the model that I should pick is the model that has the highest marginal likelihood for that data point, because it means it's not too complicated because the green one's lower. It's not too simple because the blue one's lower. It's just right. So that's the idea behind this plot. So effectively, this is where the notion that some people say that the marginal likelihood implements Occam's razor. So Occam's razor being, all things being equal, the simplest solution tends to be the best one. So that's the idea. So this is great, right? How nice is this? We can just integrate, find our marginal likelihood, and we can pick the simplest model. But to me, this is a little bit more complicated than this, because what is simple? What is the notion of simple? So I like to use this example. If you haven't seen this film, I think you should see it. It's called Behind the Curve, and it's about people who believe in a flat Earth. It's on Netflix. They do their reasoning completely through Occam's razor all the time. So you have a physical phenomena. They have a model of the world. Their model explains the data perfectly. I can also explain that data with my model. Their reason for not accepting that the Earth is a sphere is that they think it's a too complicated explanation. They simply use Occam's razor to exclude this. And this kind of comes back to me, or it manifests itself in this graph by the x-axis. So the big question here is that the data is ordered according to how complex it is. So what is complex? Complex is not an objective measure. So first, you have to somehow define what you mean by simple. But if you define what you mean by simple, this is a very sensible approach to do. What we've done is that I put a worksheet up with some more comments on this and just try to get thinking a little bit around these points. Cool. So now, if we think we can define a notion of simplicity, then we could then use the evidence to rank models. So this is really good if we agree on that. So let's try and compute the evidence for a couple of models. So first thing we're going to do is that we're going to make something, we're going to take our regression example one step further. So if you haven't seen graphical models, this is just a way of parameterizing a joint distribution. This here is the model that we used all the time yesterday when we looked at Gaussian processes. So the only thing it says is this, is that I have some data, yi. Now, yi comes from a function, fi, and that defined a likelihood. So to give yi, I only need the fi. So this plate here shows that there's a product around that probability. Then this Gaussian process was defined by some parameters to the covariance and the mean function. These are here theta. And then this whole process was indexed by a variable that was not random, which was x. X was known, right, where I took the slice along the real line. So my marginal in this case was p of y given x. This was the thing when I marginalized out everything I had a belief in, which was f, okay, and possibly theta. So now we can take this one step further and say that actually, let's say that we don't have x. We want to do what people call unsupervised learning instead. So I don't have any x. What I want to learn is that I want to learn both the function and the input to the function. Now I want to integrate out all these things, and that leads me to a marginal likelihood. That's p of y. Okay, so now regression was then this task, while this unsupervised learning was this task. At first, I just want to say that I think unsupervised learning is the biggest misnomer there can be, because it should be called more supervised learning instead, because what you actually do have is that you see the difference from these two. What is it that I've added? Well, I've added a belief over x. So it's just more supervised, right? I've added more knowledge to this problem. So it should be more supervised learning than unsupervised learning. So now this is the thing that we want to integrate. So I now want to take my input locations. I want to integrate them through this Gaussian process prior, and then I want to take this likelihood. So let's just show why this is a sensible thing to do. And the model that I'm going to explain is a model called the Gaussian process latent variable model, which Neil invented. So let's look at just the task here. So what we have is that I now do regression where I don't know the input, I only know the output. So my task is to basically take these stars, or take these data points, and you can think of it as an abacus, where I'm basically supposed to slide these stars out to the right and give them each an x value and connect the function through them. So something like that, right? Now we're going to use a Gaussian process to do that. So it will more look like something like this, right? So here I found the functions, and I've also given them an x location. The nice thing is that I can have a prior over the functions, which allows me to say that actually I don't really like this. I like this more, or I like this more. And this thing here, I don't like at all, because this doesn't fit my GP prior. Cool. So that means the thing that we want to solve to get the marginal likelihood is that we specify a prior that describes our beliefs and assumptions. And if you want to take the notion I had about the x-axis in the Mackay plot, a notion of complexity in the function. And then I express x, which is the same thing for my input location. So now let's just integrate, right? Should be fairly easy. So let's just think what this actually is then. So let's start with our GP prior, this thing here. So let's just think about the integral over x. So the GP prior is a Gaussian. So it has a covariance that sits in the exponential, and the covariance is a matrix that's inverted. Each element of the covariance is where x comes in, and x therefore might, if I have an exponential covariance, sit in the exponential itself. Then I have a likelihood where the likelihood itself might be Gaussian, so it's also some exponential. Now this integral is just completely intractable. You can't solve this thing for a general structure over x. Say, for example, if you specify a Gaussian x. So you have a Gaussian blob, and then you're supposed to take this blob through a general function. It would be very, very surprising that what you get out on the outside is something that you can actually always parameterize. So this integral is what we call analytically intractable. So now comes my third quote of Laplace. Apparently, he said, nature laughs at the difficulties of integration. And integration is, someone also said to me, derivation is a task, integration is an art. And there's a nice XKCD plot about this, if you want that. So that's a problem. You can see we just added something very, very simple to our regression model, and it became analytically intractable straight away. Then the next thing that I wanted to highlight was another intractability. So let's say we're going to do image segmentation. So image segmentation would then imply I take an image, and I think there's a foreground and a background that I want to separate. If we would build a model for this, you would normally build something like a Markov random field. So what I have here is that I got pixels, y. Each pixel has a label, x, which is foreground or background. I have a likelihood function that tells me if I know it's foreground or background, this is the colors that I think I observe. And then I have a prior, which says that if I think this is foreground, I probably think this is foreground as well. So I have some prior that makes this smooth. Okay. So now, if we would want to compute the evidence using a model like this for image segmentation. So that means that our integral is now just this sum, because I have a discrete set of possible states of this variable x. So x here is just a binary image. And then I want to take each binary image, and I want to just sum them up through how likely they are. So now, let's just take a 3 megapixel image. That's not a very large image today. That has this many elements in the for loop that sum will have to go around. So the number of atoms in the universe is apparently this number. I looked up online. Apparently the age of the universe in seconds is apparently this. So if you agree with me that writing a for loop over this number of elements is simply not possible. So this is something that is computationally intractable. So I've just given you 2 examples of very, very simple models where we directly ran into intractabilities. So either it's computationally where I have too many states to sum over, or it's analytic where there is no closed form for the distribution that I get. So effectively, this is something that happens pretty much straight away when we start making more interesting models. So what we're going to do now is that we're going to try and move ourselves out from the fairyland that we've lived in so far, where we've just looked at conjugate models. Interesting models are very rarely conjugate. One of the cool things with GPs is that they're still useful, but we can do this nice math. But very soon, even with GPs, we end up in a state where we can't compute these things. So it's absolutely impossible to give one lecture on approximate inference, which is what I'm going to talk about, how we can approximate the evidence. This is something that we should give a whole course on, and I think there probably is. But at the same time, we would feel bad if we didn't talk about it at all. So the aim of this, the reminder of this lecture, is to kind of give a flavor of things that exist and how people actually think about this. And I still think that it's very, very important that when you build models, you don't think about if the model can be solved or not. Build the right model according to your beliefs first, and then think about what you have to change with the model to make it possible to do inference with it. So we hope to give you a little bit of a flavor of approaches here. Cool. So I'm going to first talk a little bit about stochastic inference. So there's 2 main lines of way of thinking about inference, and the first one is to do stochastic, and then afterwards we're going to talk about deterministic approaches to this. So when you do stochastic inference, the problem that we're going to set up is that we have some integral here that we can't compute. And the idea of doing a stochastic inference is that, we try and replace this thing with a sum instead. So we replace this thing with a sum. If I would have the right distribution P to take this over, then this here, the approximation by approximating this as a sum, would have the same expectation, and the variance would shrink with the linearly with the number of samples. So it shrinks quite slowly, but it still works. So that's the foundation for this, of how we're going to think about this. Cool. So the first thing that we're going to use is that how can I even draw samples from any distribution in a computer? How is it even possible to draw samples at all? So this is the first element that we need. So say that I want to draw samples from this red distribution here. Now, if I can describe the cumulative distribution of this function, which is the blue line, the way I can draw samples from this function is to draw from a uniform distribution between 0 and 1. So think along y. So I draw a value here, and then I push that value through this function, and now those values will now be samples from the red distribution. So as long as I have if I can formulate the cumulative distribution, then I can always draw samples from a uniform distribution and get them to any distribution. So that's the first step we need. So now, if I'm able to transform samples from a distribution that I know that I can formulate the cumulative distribution, then the next thing is, how do I draw samples from distributions that I do not know the form of? And I'm just going to give you 2 or 3 ideas of how this can work. So the first thing you can think of, the first approach, is something called rejection sampling. So rejection sampling implies this. So now I have my red distribution again, using this example throughout, I think. Then what I do is that I now pick a distribution that I know I can draw samples from. That's the blue one. And then I multiply this with a value so that I know that this blue distribution is always above or equal to the red distribution. Then I draw a sample from the blue distribution. So that came out 3. And then what I do is now I draw a sample, a uniform sample between 0 and the value of that blue distribution up there. Now, because I'm able to evaluate the red distribution, if that sample ends up above the red distribution, I reject the black point. If it ends up below, I accept it. So now this thing here, you can do, so now you just draw another sample, and eventually these samples will have come from the red distribution. So now the tricky thing with this is, first, if you've got a massive gap like you got over here or over here, you will pretty much reject everything, and it will be incredibly inefficient to do. But it's quite easy to formulate this. So the other thing, so in this case, we get samples directly. So another approach is to do something called importance sampling. So in importance sampling, what you try to do is you try to approximate the expectation directly. So if I got this expectation over a function, over this distribution P, I can evaluate P, but I don't know its form. So now what I can do is I can add another distribution Q to this. I've made no difference to this at all. And then I can move one Q and say that actually what this here is now an expectation over the distribution Q over this object instead. So now what we can call this object here is now the relevance of a sample. So if I now take this expectation, convert it to a sum, what I do is that I first draw a sample from Q and then evaluate F there. And then I have a relevance value, which if Q is much larger than P, should be downscaled. And if the other way around, it should be upscaled. So yeah, which was shown there. So it's just simply something like this. Now I pick my two distributions. I draw a sample from the blue one, say it's here. Then that sample is not very representative of the red. It's more representative of the blue, so therefore it should be down-valued. In this case, that sample should be up-valued. So the benefit of this approach is that you reject no samples, right? Cool. So that was two simple approaches that are super easy to formulate, that can be incredibly inefficient, but can also be efficient if you got a good proposal distribution. So the next thing which you can look at is to actually say, rather than drawing these very simple distributions that we had, can you have a conditional distribution that you draw from? Can you have a conditional distribution that allows you to explore the space a bit better? So when you've drawn one sample, you draw the next sample based on where you drew the previous sample. And this is something called Markov chain Monte Carlo. So in this case, we start with a state, x0. Now that's just a random initial state. And then I have now a conditional proposal distribution. So what I do in this case is that I now draw a state x star from this distribution that I've specified. Then I compute an acceptance probability, which says that if the relationship, if the point that I'm having, the x star that I drew, is more probable under the true distribution, then the minimum of this is going to be 1, right? If it's less probable, I get a smaller value out here. So that's A. That's my acceptance probability. And then I draw a uniform number between 0 and 1. And based on if this uniform number is larger or smaller than this acceptance probability, then I accept this as my new state. So as you can see, that means that you accept every value that takes you to a higher probable state, but also sometimes due to this sample, you also accept samples that take you to a worse place. So this allows you to explore a little bit as well. So if it's not, then you reject and start over. So this thing is very often very useful, and it's nice because they have very nice guarantees in the limit, and it's this acceptance probability allows you to explore the space. So what I'm going to do now, because we're running a little bit out of time, I'm going to do just quickly summarize sampling. There's tons of different sampling methods that you can apply. Now, most of these methods provides a guarantee in the limit, but very often it requires a lot of problem knowledge to make these efficient. But there are toolboxes that you can kind of use state of the art where there is a ton of heuristics that allows you to still do this reasonably efficiently. So now I'm just gonna do, we got 10 minutes more. So I'm gonna do the other way of thinking about inference, which would be deterministic inference. So now we're gonna take a completely different approach to the problem of finding the evidence. So now let's look again at graphical models. So now I have some model of some data y, and it has this latent variable x that I want to integrate out. So this here is the object that I want, right? So I want to compute this integral here. Can't compute this integral, but there's another way of writing this object, right? Is that I can write base rule, and I can write it in a bit of a strange way, right? So I can write base rule as the likelihood times the prior divided by the posterior, which is equal then to the evidence. So now you can effectively equate of saying, well, if I have the evidence, then I can get the posterior. That's how we've seen it so far. But you can also say, if I have the posterior, I also have the evidence. So we're going to change our problem into a search for the posterior distribution instead. And what we're going to do is that we're going to formulate an approximation to the posterior. We're going to do it in this way. We're going to say that there is a approximate distribution Q, which I specify, which has some parameters theta, which is the parameter we're going to try and learn. And we're going to try and find this so that this matches the posterior. Because this distribution does not contain y, what that means is that this variable theta needs to represent all the information about x that y contains. So that's the idea. So let's start then with the object that we want to approximate. So P of y is what we're after. So now we're going to work with log P of y because it makes life a lot easier. So now we can write up log P of y, and then now we wanted to connect this to the posterior. So I'm going to write up this quite useless integral, which is just the posterior over the posterior. So I'm just integrating this, nothing happens. And then what I'm going to do is that now I want to put these two under the same integral. So what I'm going to do is that I'm going to add another distribution, q of x, and this is the q of x that we're going to later use. This is still the same, so now I'm just integrating this over q of x as well. So what I can now do is I can put these two within the same integral. So that leads me to this. So now up here, I got the posterior times the evidence divided by the posterior. Now this here is the joint distribution, right? So what I'm going to do now is that I'm going to split this integral and I'm going to add an additional q of x, so something that does nothing. So what I have now is that I have the q of x integrated over the joint distribution, and I have this term q of x and the posterior, which comes down here, and then I have this q of x here, which I just added that does nothing. Now I'm going to distribute these q of x's over to this integral over there. So that leads me to these three objects. So now I got the first term, which is just the integral over something which we haven't even specified yet, q of x. And then I got another one, which is q of x log p of x, comma y, so the joint distribution. And then I got this term, which is the only term that contains the object that I don't know, which is p of x given y. So let's look at this term first. So to do that, we're going to need to do a little trick. We are going to need to use what's called the Jensen inequality, which is very simple. So it just says that if I got this convex function, and now obviously this is the definition of a convex function, and now if I take a point in between these, I'm always going to be above the convex function. So what that means for integrals is that if I take the expectation of a convex function, it's always larger than the function of the expectation. Now the function that we're going to use is a log, so it's not convex, it's concave, so we just get the opposite behavior. So what that means is that I take the log x, I integrate that, that's always smaller than the log of the integral. So moving the log inside the integral makes it the lower bound on the integral. So then let's look at this thing that contains the posterior. So if I now first flip them around, and then now I can see if I move the log out, then these q of x's just disappear, and I get this distribution here, integrating the posterior over x. It's just a distribution, so it has to sum to 1, so I get this to 0. Then, so I know that it's always lower bounded by 0. So I know that the red term is always larger than 0. And then what we can do as well is that we can say what happens if q of x is equal to p of x given y. So now this just gives me a integral log of 1, so it becomes 0. So that term there is what some of you might know as the KL divergence. So it's a measure of divergence between distributions. It's not a metric, but it's 0 if q of x, if the two distributions are equal, and it's always positive. So now this leads us, I'm going to skip the blue term because that's just showing the same thing. So this leads us to this thing. So we started off with log p of y, and we have the blue terms and the red terms. The red term is the term that contains the object which we can't compute, which is the posterior that we're actually looking for. As I know that this term is always positive, and it's 0 only when q of x is equal to this, I can now effectively drop this and say that that means that this term here is a lower bound on this. And this bound is tight if q of x is equal to the posterior. So what I now have is that I have an optimization problem where I can try and maximize this lower bound. And by maximizing this lower bound with respect to q, I'm now going to find a good approximation q to the posterior. So in effect, this is what we have. I got log p of y, and I know that this consists of these two terms, and this term is always positive, which means what we're going to try and do is maximize the blue term. Try and find a q that maximizes this. So I know that I'm running massively out of time, so I'm just going to jump very quickly to the summary. There was not much more, there was just a specific case that I was going to go through. So the thing with variational base is that because we specify q, it's never exact. Where the sampling methods are exact in the limit, variational base is never exact. Because if you have an intractable, analytically intractable posterior, you clearly can't find a tractable formulation of that, right? So it can be made very fast, and there is existing exciting work at the moment looking at mixing sampling and variational inference by making implicit variational distributions. So just a very, very brief summary of what we tried to get across. So talking about the evidence, it allows you to do model selection, but you have to think about the concept of simple. I put a worksheet up on the evidence that hopefully highlights a few more of these things. So most interesting things are intractable, and this leads you to this field of approximate inference. The aim of today's lecture was to give you a hint of a couple of things of how you can think of this and basically the big schools of thought. But there is also an additional thing. How about we would treat this whole thing as an inference problem instead? Let's just think about it, right? You can sample the integrand. Well, that's data. you kind of have an idea of the integral. Well, if the distribution, it sums to 1, right? That's knowledge. Well, that could be your prior. You would be able to come up with an integral and match it to data. That's kind of a likelihood, right? So maybe you can think about this whole thing as a machine learning inference problem instead. You can maybe build a model of this computation itself. And with that, I'm going to end, and I'm sorry that I dragged on for a little bit too long. Cool. I'm going to stop sharing now.
Okay, and I'm going to stop the recording, give people a chance to see if there's any questions they had if we run a bit.